All right, so for our second problem, we are going to look at um, something called a re-entrant exit. A re-entrant exit is an exit that protrudes into the tank itself. Um, and these often happen when you have you drill a hole in the tank, stick a tube in, and then seal around the tube. That's a re-entrant exit. So these are the cheapest way to make a hole at the bottom of a tank. And it turns out when you do this and the water drains out of the tank, the water leaves at a diameter or an area that is smaller than the area of the exit. And our question is what is the area of that exit and what is the velocity of the jet? Right off the bat, you should know we have two unknowns, which means we're probably going to need at least two models to solve this problem. And what makes this problem particularly difficult is it's not immediately obvious which model we're going to use. And so we have to, the question is now is what question do we ask ourselves to help choose a model to start with? So in this case, we don't have a lot of small pipes. We don't have a lot of high velocity gradients. So we can probably use Bernoulli's to calculate pressures. So we have pressures, we have velocities for sure, we have areas. So what model do we have that can handle pressures, velocities, and areas? And the answer is conservation of linear momentum. So we're going to start with that and try that. So let's write out conservation of linear momentum. Sum of the forces is equal to the integral over our control volume of rho v xyz dv plus integral over our control surface of rho v xyz w dot n hat dA. Great. So now step one, the second we write down conservation of linear momentum, we have to draw a control volume. In this case, I'm going to draw a control volume that goes along the back side of our tank, comes across far enough away from our exit on the bottom that the water is basically still, and then comes up, cuts through our re-entrant exit, cuts through our jet, and then cuts back across to the left-hand side of our tank at far enough above the re-entrant nozzle that our fluid is entering almost universally downward. Because remember, we're trying to choose control volumes where we know things, right? Where we know things. And so if the fluid flow near the nozzle is quite complex, right? We have flow coming at an angle around this corner and around this corner. So we want to stay away from those corners as much as we can with our control volume. Wonderful. And great. Now we got to pick a direction. Well, our flow is leaving in the x direction, and so clearly we're having acceleration of our fluid in that direction and forces in that direction. So we're going to pick. By the way, I didn't write this down, but step one was draw a CV and coordinate system. So we got to draw our coordinate system, and I'm just going to draw it on our control volume. Actually, it doesn't matter. Our control volume is not moving, so I'm going to draw it over here on the right-hand side. X, Y, Z. So step two, pick a direction, write down and simplify your assumptions. So we pick a direction. We're going to pick a direction, write assumptions. All right, so we're going to pick the x direction because that's the way our fluid is flowing. So we're going to pick sum of the forces in the x direction is equal to d dt integral of Vx times rho dv plus integral over our control surface. The first one is integral over our control volume, but our second integral is over our control surface of rho vx w dot n hat dA. And we are going to assume for this problem, and then why don't you pause this and try to guess these assumptions ahead of time. We're going to assume uniform flow, and the entrances and exits of our control volume. We're going to assume our density is equal to a constant. That's pretty reasonable. This looks like water. This next assumption is not what I would call questionable, but not immediately clear. I would assume steady state. And the reason I assume steady state is that the rate at which we're going to assume the rate at which the tank height changes is small compared to everything else, so it doesn't matter. So we're going to assume steady state. We'll call this A, B, and C, and we're going to use gauge pressure. So we're going to call that D. Awesome. So step 3 is simplify and solve. Well, if we look at our forces, we have pressure on our tank in this direction on these faces, our pressure on our control volume. Remember, pressure always acts inward on a control volume, even though we're right up against the edge of the tank with our control volume on the right-hand side. We still have a pressure acting everywhere but the re-entrant exit. On the left-hand side, we have pressure acting also inward, and the only place where the pressures don't cancel out is on the area here that corresponds to the re-entrant exit. So if we add our forces in, we're going to have some of our forces in the x direction is equal to pressure times area exit. And it's acting in the positive direction in that one little area that doesn't cancel out, right here. This is A, exit there. Acting in the positive direction, so we're going to leave it positive, and that's equal to V jet. Oops, hold on. I meant to write rho first, sorry. It's equal to rho times, now we have to do Vx. In that case, it's going to be V jet. And we have to do w dot n hat now for our exit. Remember, and the whole reason we have to go straight to rho v jet w dot n hat times a is because we have both uniform flow and density is equal to a constant. So our integral goes away, and we now just sum up the entrances and exits of our control volume. So, and let's label this just because I want to do some extra stuff here. It's 1 and 2 and 3. So we have vjet, which is our Vx, and then we're leaving perpendicular to control volume, so it's plus or minus the velocity for the dot product. And since it's leaving, it's positive, so it's just going to be Vjet times the Ajet. Great. And we now we're going to do, that was 1. Now let's do 2. And 2 is actually really easy because we've assumed that all the fluid is coming in straight down, right? We've drawn our control volume far enough away that this is a reasonable assumption. So in that case, we have rho times our Vx is 0. Our w dot n hat is something we don't know, but it's going to be a negative w. We don't know what the velocity is there, times a top. But it doesn't matter, right, because this whole thing is 0 because the Vx is 0. And the same is true of 3. Our entrance at the bottom, we have rho times 0 times something. Actually, it's really quite small. It might as well be 0, so the whole thing is 0. Wonderful. So if we go through, and I recommend you do this all the time, look at the things you don't know and what you do know. We do know A exit. We do not know A jet. We do know rho, We do not know V jet. And we do not know P. So we actually have three unknowns here. We have we have density, pressure, velocity, and A jet, which we do not know. So that if we have three unknowns, that is the worst written three ever. Three unknowns, we need two additional constraints on our problem here. So we need a model that relates pressures, heights, and velocities. This one you guys should know. And the reason is, we've done it before. We need Bernoulli's. So we have to make an additional assumption in order to use Bernoulli's, right? And that assumption is we need to assume an inviscid flow. So let's go down here and write assumption E, inviscid. And with Bernoulli's, if we write it out here, P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. With Bernoulli's, we have to write a streamline, right? So the equivalent of a control volume for Bernoulli's is streamline. So let's draw our streamline. And in fact, we're going to use it twice. Okay, the first time we're going to use it, we're going to solve for a pressure. I'm going to use green for the streamline. We're going to go up from the top. We love going from the top of tanks because we know the pressure and the velocity there. The velocity is basically zero. The pressure is atmospheric pressure. And we're going to go first down here to immediately in the middle right here for A of our area on the left-hand side where our pressure does not cancel out. We'll call this point 1 and this point 2 over here. And then we were also going to go down and over to here to the right-hand side into our exit velocity, into the exiting jet. And we're going to call that point 3. And we're going to use that streamline in order to find the exit velocity of the jet. So let's do the first one, which is the finding the pressure. So if we apply it towards finding the pressure, if we we'll call this equation 1, if we simplify it to equation 2, we see that at the top of our tank, our velocity is basically 0. Our pressure is atmospheric, so it is 0. And we get that GZ1 is equal to P2 over rho. And the reason for that is our V2 is also basically equal to 0 in this problem because it is right up next to the wall. And any of the fast velocities are heading in the x direction on the other side of the tank. So we can pull this rho over here and solve for our P2. And our P2 then is equal to we're going to leave it like that. Sorry, my bad. We're going to leave it. P2 is equal to rho G times H. We can also solve this for our point 3 to find our velocity exit. So we're going to do, for that one, we do the exact same thing. The left-hand side now, so 1 to 3. Our left-hand side is just GZ1, and then our right-hand side, we're in a free jet, so our pressure is still atmospheric pressure, so our pressure on the right-hand side is 0 gauge, but we have a non-zero V2. That's going to be equal to V3 squared over 2. So what we're saying basically is here, our height is at a 0, and our pressure is at 0 because of gauge pressure, but we do have energy in our velocity, our kinetic energy. Great. So we can solve for V3, and when we do that, 3 to 4, our V3, which is equal to our V exit, is equal to the square root of 2GH. Excellent. So if we combine all of these equations, if we combine 2, 4, and our, we'll call this equation 0 because I forgot to label it, 0, 2, and 4, if we combine 0, 2, and 4, we now have 3 equations. We had 3 unknowns, so now we can put it all together, and we get that our pressure is rho GH times A exit, which is equal to square root of 2GH squared times rho times A jet, which is great because actually we can cancel out the rho, the G, and the H. And we can solve for the fact that, and this just becomes a 2, right? Because the square root of 2 squared is 2. So we can solve for the fact that our A jet is just equal to our A exit divided by 2, which is just a fascinatingly simple answer, right? So it turns out that when you have a re-entrant exit, when we just cut a hole in the side of our tank and stick a pipe in and then put some glue around the side and call it a day, the exit that our jet leaves our tank is half the area of our pipe, which is terrible, right? Because presumably you're trying to get fluid out of a tank, which means you're getting half the fluid out, half the flow rate that you think you should. And the question I want to ask before we sign off on this video is, why a re-entrant exit has a lower area, and then why a curved exit like the one shown here would not have an area decrease. And the reason is, and we've talked about this before, the reason that a re-entrant exit has a smaller exit area than a smaller jet area than the exit area is that as the water comes around this corner here, it can't make this corner at it can't make a 180 degree turn, right? It's just like a car. It has to have some kind of radius to its turn. And so when it comes around this corner, it has some y momentum that then carries it past to the point where it comes out over here and narrows down the jet. And so we can reduce that by creating a curved entrance to our pipe, in which case we gently convert that y momentum here, I'll do it in red, that y momentum into x momentum so that when it leaves our pipe, it's all in the x direction. And these are expensive though because you have to cut a hole in your tank and then carefully weld a curved piece of piping in, which is, not great. If you want to think about it in terms of the problem that we're looking at problem that the way we solved it up here, if you want to think about it in terms of the conservation of linear momentum, why a curved entrance does not have a smaller area, the reason is because up here at the top and bottom we have a non-zero velocity, so the pressure is lower. Before, when we had the re-entrant nozzle come in, this velocity is basically 0, but it's lower, pressure's lower here, so we have we can't cancel out the pressures like we did above and outside of the nozzle, so we end up having we have a bigger pressure difference between the left and right hand side, so we need more mass flow rate in order to counteract the difference in pressures. So cool, it's kind of a cool problem, which leads to an unexpected answer, which is that your area of your jet is 1/2 the area of your exit.